Okay, everyone, this is just a sound check. Can you give me a +1 in the chat if you can hear me? And if you can see the timer, as you can see, we will be starting very soon. Okay, that's my call to start the stream. Okay, great, thanks. So, okay, so let me just get started by hi, good morning. It's great to see so many of you here. As I said, I'm mostly doing this to make sure that my live stream setup makes sense and is smooth for an upcoming course. So those of you who are here independently, thanks for joining. Those of you who are here because you're curious about DSA 2, feel free to drop in any questions you have in the chat. But the agenda for today's stream is going to be to solve this um, specific problem on Codechef, which is based on a classic and a really fun problem to think about called the stable marriage problem. So let me see if I can pull that up for you. Just give me a minute. So there is a link in the live chat, so you could head over there and start to take a look. But let me see if I can also get it in the stream. Okay, I should have prepared this earlier, but okay, let's see. It's cool. You're going to worry about the input and output format in just a bit, but okay. So on the left of the screen, you can probably see sort of a sample input. We will get to that later. Let's not worry about it for now, but let's just try and talk about the problem itself. Okay. So you're given n men and n women in this situation, and every man and every woman has a ranking over the other group. Okay. So for every woman, she has a choice of her most preferred partner and then her second favorite, and so on and so forth, until the very last preference. So, one thing to keep in mind is that these are complete rankings, which is to say that a woman ranks every man, even if even if she does not like somebody at all, they still feature somewhere in the ranking. So these are not partial rankings, okay? And this happens for the men as well. All men rank all the women in order of preference. And another thing to keep in mind is that these are strict preferences, so there are no ties, right? Um, and given this setting, you want to get the men and women married to each other, married in quotes. The idea is to come up with pairings of men and women with each other in a particular way. So you want to make sure that it's a nice marriage. And so I think the idea is to try and understand or define what makes for a happy marriage. So, any suggestions in the chat for, so there is, of course, the problem statement, which has one suggestion. The suggestion in the problem statement is that, nobody will want to basically run away with somebody else. that's the idea of, finding a stable marriage. As you can see, the name of the problem is stable marriages. But if you have any other ideas for how you might want to, think about a happy marriage, feel free to drop that in the chat. It'll be interesting to explore what is your idea of, what makes for a happy marriage. Okay, meanwhile, okay, let me just make a couple of corrections here. Okay, so I see that there are. Okay, let me just switch over to my notes so that I can visualize this for you a little bit. And you might want to already think about what is the stability condition, what does it tell us? And let's see. Okay, so let me just momentarily test the camera. Okay, it seems to be working, but I'm also obstructing the notes, so let me get out of the way. Okay. Okay, question in the chat. Can we use a stack to represent the woman and then append an array for the men? Yeah, we will be using a lot of lists and arrays and things like that. But even before we get to the data structure part of it, where I think you're thinking about how do we handle this information, we want to get some clarity about what is the target, what are we trying to find, what is the optimization goal, and how do we find it, right? So just to recall once again, this is the setting. You have n men and n women, and each man has a ranking of the woman, and each woman has a ranking of the men. So this is in fact the first example that's in the problem statement. So for example, so the blue numbers denote the men, the orange numbers denote the woman. And so for example, the man labeled 1 ranks the woman as like 3 is the top preference, and then 2, and then 4, and then 1, and so on and so forth, right? But here is the goal. The goal is to come up with a pairing of each man with a woman. Okay, so right, a couple of comments in the chat where the last two lines are unclear, and Meet is asking if we can make two dictionaries. Yes, I think we're definitely going to get to the implementation details very soon. But as I said, let's first just try and figure out what is it that we are trying to do. So we're trying to come up with a pairing, right? So we want to match every man to a woman. So let's say, for instance, you might want to say that you match. So what if we just try the matching by same labels? So 1 gets matched to 1, 2 gets matched to 2, 3 gets matched to 3, and 4 gets matched to 4. Is there something problematic with this matching? Why would you say that this is not probably a good matching, or maybe you say this is a good matching? There's some of it which looks nice and some of it which looks pretty bad. Can somebody point out what are the problems? Okay, so let me point out that person 2, or the man who is labeled 2, is getting matched with his top preference. So this is a good situation for him, and in fact it's a good situation for the partner as well, because they seem to mutually like each other rather a lot. So they're each other's top preferences in this case, and this part of the matching is a happy one. But if you look at M1, or the man that we are calling 1, is matched to 1, which is sort of their worst preference at this point, and they would rather be with almost anybody else. And if you look at the partner as well, she's not terribly thrilled about it either, because 1 is her second worst choice in some sense, right? So, so this is going to be one somewhat unhappy couple. So let's say the man who is labeled 1 would rather be matched to any one of 3, 2, or 4. And well, I mean, 2 is going to be tough luck because 2 is already happy in her own marriage. But let's look at 3 or 4. In particular, let's look at 3, right? So 3 is 1's top choice. And if you look at who 3 is currently matched to, is currently matched to 3, which is, it's okay, it's her second choice, but she would rather be with 1, right? She would rather be with 1. So, so if 1 and 3 decide to, discover that, or they find out that they like each other more than they like their current partners, right? So, let me point out again that 3 is currently matched to 3, and 4 is currently matched to 4 out here, right? So as of now, we see a danger sign as far as the pairing 1-1 is concerned, because here one's favorite preference on the men's side is 3, and 3's favorite preference is also 1. So there's some mutual affection there, and they would be willing to essentially trade off their current partners for each other. And this is exactly the situation that we want to avoid, right? Okay, so right, so let me read out a suggestion that's come in the chat, which says, let's start from a man or woman and check first preference, and if that preference is the same, then we make a pair. If not, we check if the second preference is a match, and alternate from man or woman to move to the next preference. That seems like an interesting take on this, because, for instance, you will be able to catch all these mutual admiration clubs. So if a man prefers a woman, has a woman on the top and as the first preference, and that woman also enlists the same man as being her top choice, then they will essentially get associated with each other based on your algorithm. But we do have to be careful about what happens when this is not, if this is not mutual, then instead of jumping to the second preference directly on both sides, should we try and make some tentative arrangements and then try to sort of explore this further? So that's the question that we want to explore. Okay, so let me just emphasize the main idea that will be, kind of the point of this problem, is to try and recover a pairing which is stable. So just to recap, what is stability? If you propose a pairing, so again, just to be clear, what is a pairing? A pairing is an association of men and women. So for every man, you want to find exactly one woman. All right, so that, well, of course, you want to make sure that it's mutual. So every woman is also associated with exactly one man. So if you think of these two as sets, what you're really looking for can be thought of as a bijection. So every person is associated with exactly one other person from both perspectives. And what you want is that the following situation does not arise. So the situation that you can see on your screen here is the sort of thing that we encountered earlier, and we said this was not a happy situation. So let's say M1 is matched to W1 and M2 is matched to W2. In the context of this problem, you might even say something like M1 is married to W1 and M2 is married to W2. But let's say that in terms of preferences, M1 prefers W2 over W1. That is to say, he prefers another person over his current partner. And if we go to that person, then we see that she also happens to prefer M1 over M2, which is to say that she reciprocates in thinking that this person M1 is better than her current partner. Then this is not a stable marriage, because in this case, M1 and M2 are very likely to get together, breaking their current marriages, speaking purely in terms of preferences, right? So we want to avoid this situation, and we want to, in other words, so if you think of the way this is stated in the Codechef problem statement, you will see that what they're saying is that If M1 is matched to W1 and there is someone that M1 likes more than his current partner, then that person does not reciprocate this love. Okay, so then W2 prefers her current partner over M1. Therefore, there is no risk of M1 eloping with W2. Okay, so is the target clear? Give me a +1 in the chat if you're still tuned in, and if the problem statement is clear. You want to come up with a marriage where this criteria is true for all possible choices of M1 and W2. Okay, great. I see at least one confirmation, so I'm going to take that as a sign to move on. Of course, if you have a question, please feel free to share your question as well. By the way, sorry, I think I forgot to see that there is another question up there. Who has initially married? Yeah, so there isn't any initial marriage meet. So right now we are starting with a blank slate, and we need to kind of establish a pairing. Okay, so fine. It's great to see that we are on the same page. Thank you so much for the responses. Um, Now let's actually talk about a potential solution here. So what I'm going to share with you is a classic algorithm for finding these stable marriages. It would be really nice to have a discussion about potential ideas for how you find such a marriage. I think there have been a couple of suggestions already, but because we want to, some of my focus here is in getting to the implementation. And also, by the way, this is going to be the spirit in which we're going to be doing a lot of DSA2. For those of you who are here because you're curious about DSA2, we will still be doing a flipped classroom, meaning you will be looking at some lectures in advance of the class, but in the classes, we're going to spend most of our time actually implementing the algorithmic ideas that you look at. If you have any suggestions at this point, the course is going to start only in January. So if you have any ideas, then please feel free to share. But because the emphasis here is on actually implementing this algorithm, I'm just going to, like, this is a spoiler alert. I'm just going to tell you what the algorithm is. But if you have any suggestions, please feel free to share them in the chat. Okay. All right. So I'm going to share with you what is called the men proposing algorithm. And this is not by any means, a sexist formulation. It's algorithmically completely symmetric. You could also set it up so that it's a woman proposing algorithm, but I'm just going to go with this because that's the standard description in the literature. But there's some very interesting technical points about what changes if you go to the other version, and maybe I'll make some comments about that towards the end. But for now, let's understand some algorithm, right? Okay, so all right, yeah, so it's a good point. Dhaivat's saying that there is like a 10-15 second lag. That is true. That's a good point. So I'm going to just be patient in waiting for the responses. Absolutely. Okay, so the idea is going to be the following. What the men are going to do is that they are going to propose to, in some sense, the current best person on their list. So the current best will make sense when we talk about what happens as we go along. But to begin with, what's happening is that all the men propose to the top person on their list. So this is a bold move, just that they're going to go for. That they're going to try and get the best possible match that they can hope for, because it doesn't hurt to ask, hopefully. So that's what they're going to do. From the woman's perspective, what happens is that when this happens, some women potentially get multiple proposals, and some women don't get any proposals at all. It might be that all the women are nicely distributed on the top. So it's possible that, if you look at the top choices, it's essentially a permutation of 1 to n. And if it is that, then that's a very happy situation, because everybody has a distinct top preference, and then, everybody just gets their top preference. And you can check for yourself that if everybody is matched to their top preference, then you never have a situation like this, because there is no question of what if I like somebody else better than my matched partner, because my matched partner is actually the best person that I could have hoped for. So that's a easy case, but unfortunately reality is often not so clean. So you might be in a situation where there are some popular choices of partners. So some people may get multiple proposals, whereas some people don't get any proposals at all because they don't appear as the top choices on anybody's list. And by the way, although we're going to be continuing to use this man-woman sort of terminology because that's how it's also stated on the Codechef problem, you can imagine that this applies to any setting where there are two parties who are trying to figure out what's a good match. So JE admissions would be an example. So there are, one side, it's not quite so equal and cut out, but it's roughly the setting, right? So on the one hand, you have the institutions that use the JE rank to determine admissions, and on the other hand, you have the students who also have rankings over the institutions. So they have their own set of preferences. And it's, of course, a very pertinent question as to how do you match? And this is actually a version of this problem with capacity constraints, because, it's not that you want to match you want to get an exact pairing, but you want to match a certain number of students to every institute. So some tweaking, but I just wanted to pause to say that this is a situation that you can relate to in many settings. It's quite fundamental. But anyway, coming back to this, as you can imagine, there are some people end up getting multiple proposals, some people end up getting none at the end of the first round. And what do you think the side that is receiving the proposals? I think the answer is already on your screen, and hopefully this is natural, but let me ask it anyway. So if you get multiple proposals, which one are you going to pick? Yes, exactly. So you're going to pick your best proposal. If you're getting multiple proposals, you're spoiled for choice. So you can simply pick the most preferred proposal that you're receiving, right? So in this example, for instance, 2 receives proposals from 3 and 1, and depending on which option she likes better, that's the proposal she's going to pick for a temporary engagement. That's the way this is going to work. And so we're going to build out a list of temporary engagements, and let's see what happens after this first round. So after this first round, you can imagine that some men got rejected. They made a proposal, but unfortunately the person they proposed to had multiple proposals to choose from, and they did not get selected. And yeah, this may be uh, this algorithm is surprisingly relatable on many levels. But anyway, the point is, yeah, so the point is that might happen, in which case you go back to being, you go back to square one where you started, you're still single. And what you do now is, like it was being suggested in the chat earlier, you move on in your list and you move to your second favorite proposal, for instance, or your second favorite preference on your list. And and you continue to propose. So you just try again, and the same scene is going to play out with a small difference, which is that to begin with, all the women were also single. But now, when women start receiving proposals, it's possible that they are already in an engagement from a previous step. And if that is the case, if they are in an engagement from the previous step, then what's going to happen is that, so the way women do this is super rational, or you might also say that it's a bit selfish. They're going to look at their current partner, and they're going to look at the proposals that they get, and they're again simply going to pick the best one, which is to say that if they get a proposal from a man that they like more than the person that they're matched to, they are simply going to go ahead and accept this fresh proposal, and they might possibly break a current engagement, and that is allowed in this algorithm. The woman can do that. And yeah, so that's how this is going to go. And you keep going until you basically exhaust the set of men who are single. So as long as there are men who are still single, who are not engaged to anybody yet, they're going to continue proposing. And at some point, at some point, hopefully everybody finds a match. So that's the entire algorithm. And we're going to analyze this for three things. One is, first of all, does this even stop? Do the men keep having to propose on and on forever? Or can they be ill-fated to, just be in a sort of infinite loop? Or is it that the algorithm stops after some point, at which point, hopefully, it has found a matching? And then the question we want to ask is, so does everybody get matched? And is this matching stable? Okay. So let's analyze this, but before that, let me again pause and ask if the mechanics of the algorithm itself is clear, because this is what we will be implementing. I want to spend like a few minutes on the analysis, um, but I want to make sure that the mechanics are clear, because this is where we'll be using, this is what we would like to implement. And also, for those of you who feel like it, the link to the Codechef problem is in the chat, and you now know the mechanism. Yeah, a bit of a spoiler alert is that it actually works. I haven't, there isn't anything here that where I've tried to pull a fast one. It kind of this works. So if you're feeling motivated, then please feel free to go ahead and even start coding it if you like. Okay. Okay, so good. I think I have a couple of confirmations in the chat, so let me move on. So the first question I want to ask is, how many proposals are made? If this is a finite number, this is a fixed number, then we know that the algorithm doesn't go on forever. And then after that, of course, we will talk about the outcome, and if that outcome is what we want. But can somebody tell me, overall, remember that there are n men, each of them have a ranking of n women. In the worst case, how many proposals do they make? Okay, so there are some responses already. N times m, except that, okay, so there are n men and n women. So I don't know if the m is for men there, but you'd be quite right. So essentially, what we have is a situation where there are n men, each of who is looking at a ranking of n women. And even if this were to play out in the worst case, which is that every man proposes to every woman on his list, you want to think about whether there's a situation where that can happen. But even then, we are looking at something like n squared proposals, right? The main reason for this is that men never go back on their list. So once they have been rejected by a woman that they have proposed to, in this algorithm, they're never going to propose to that woman again. Okay, not necessarily in real life, but the way the mechanics of this algorithm works is that you never go back and propose to a woman that has rejected you in the past. Okay. Anuj is saying that you did not get the question. So the question was the following. So we described this mechanism, or we described an algorithm to come up with a matching, right? So we said the way this is going to work is that the men start by proposing to the women who are their current best option. To say current best, I mean that among all the women that have not rejected them yet, they consider the woman that they like the most, and this is the person that they approach, and that is a concrete step in the algorithm. So it's a man proposing to a woman, and based on how these proposals play out, the algorithm makes progress, right? So the question was, across one run of this algorithm, of course it depends on how the preferences are structured, etc. But even in the worst case, how many proposals can you make? Because the algorithm is driven, like every step of the algorithm is a set of proposals, right? So if the set of proposals is bounded, then the algorithm also finishes in that time. We want to also say that once you run out of proposals, like there are no more proposals to be made, that we actually have a matching, and we'll get to that next. Um, right, yeah. So you're right. If n and m are different, then essentially depending on if n is greater than m or the other way around, some people are going to be left out. So they would have to be the same. That's right. Um, so Anuj, hopefully that clarifies, what the question was. And the next thing we want to think about is if everybody finds a match. So then like we know that the algorithm is going to terminate because the algorithm is driven by proposals, and we see that the number of proposals you can make is, it's bounded by n squared, as we just discussed. So when we are done and dusted, the question is, does everybody actually find a match? So what do you think? Is it possible that somebody is left out, for instance? Okay, so everyone will find a match since m is equal to n. It's sort of true. So in particular, let's say that there was a man. So by the way, there is one subtlety that I should make explicit here, which is that if a woman receives a proposal from a man and that woman is currently single, then and if this is the only proposal that she receives, she will accept it. So in particular, from the woman's point of view, being matched is being better than being single. And of course, once you are engaged, then you work with the best proposal that you get, right? And as Anuj is saying, the match that you get may not be your best possible match, but you will get some match, right? In particular, let's say that the algorithm is finished, and here is a man who is still single. Um, But because of the counting argument and the fact that we are maintaining, we have maintained a set of engagements which are essentially pairings between men and women. If there is a man who is still single, then there must also be a woman who is still single. And if a man is still single at the end of it, it also means that he proposed. He also proposed to everybody, right? This must have been the case. Because if he didn't propose to everyone, then, well, then that means that he is single, and we said that this while loop runs for as long as there are men who are, as long as such men exist who are not yet engaged. So if this man is single at the end, then he's single, then that means that he must have exhausted his list, because if he didn't exhaust his list, then the algorithm would continue. He would have somebody to propose to. So he has proposed to everyone, and in particular, he has proposed to the woman who is also still single at the end of the process. Because remember, if the process ends and there is a man who is single, then there must also be at least one woman who is single. Because if all the women are matched, then there are n women who are matched to less than n men, which is not possible. Right? So there is also a woman who is still single, and in particular, our friend here must have proposed to that woman, and that woman, when she got that proposal, would have had no reason to reject it. Because remember that if you are single at the end of the algorithm, then you are also single at any intermediate stage of the algorithm. Because if not, then you were not single and you were engaged. Then once you are engaged, you remain engaged. Because remember that you hold on to your engagements. The only reason you let go is you found a better offer. Right? So it is never the case that at some point you were engaged and then you became single. So none of the women are stupid. So they're not going to drop off a current engagement and go back to being single. So at whatever stage this man proposed to this woman, she must have been single at that point. But then if she was single and she got a proposal, she would have accepted that proposal, right? There is no reason for her to reject it. So that's a contradiction. So at the end, you cannot have a man who is still single. Okay. Cool. All right. So give me a +1 if points 1 and 2 are clear up to this point. That is to say that everyone finds a match and the algorithm terminates in quadratic time. Okay, awesome. So I think it's great that we are making sense so far. Now the question is, the main question that is left is, well, we have come up with some way of matching, but of course, coming up with some matching is not so interesting because you can come up with a matching in many ways. But we have hopefully come up with one that is stable in the sense that we wanted stability in the beginning, if you recall, right? So let's think about, is it possible that the resulting matching is not stable? Okay, the matching that is output by our mechanism, by our algorithm, can it happen that it is not stable? So if it is not stable, then that means we have this picture. We have, let's say M1 got matched to some W1, M2 got matched to W2, and M1 and M2 like each other, sorry, M1 and W2, this is a classical setting. So M1 and W2 like each other better than their current partners. Okay, so this is a situation that we said we want to avoid. And is that, can that happen? Given the algorithm did whatever it did, can it happen that we have this? This is what is called a blocking pair, by the way, this situation. Some people even call it an eloping pair, but I think the most standard term is blocking pair. So can you think about why this would not happen, right? Our mechanisms should sort of prevent this. And so let me just break the suspense and say that the matching is stable, okay? But we want to understand why. So in particular, what can we say about M1 and W2? Our point is that M1 and W2 would have sort of found each other through the mechanism before getting into these suboptimal engagements, right? So, yeah, Dhaivat, that is intuitively correct that we make a new engagement. If we get somebody better, we make a new engagement. But I think it's still good to formally argue that there is no instability because notice that in this mechanism, some women may not even receive proposals from men that they like more than their current partner, because the men got engaged sooner with somebody that was not ready to let go of them, and so on. So since it's not the case that all possible proposals happened, it's good to argue explicitly that there is that we do have stability. But the reason is kind of what you're already pointing out. So your intuition is absolutely correct, but we just want to formalize that a bit. Okay. Let me just quickly mention that that's another aspect of DSA too. We will be looking, there will be a lot of emphasis on making sure that we are convinced about why our algorithms work, usually through formal arguments for correctness. So of course we are interested in coding things up, but we also want to be sure that we are coding up the right things. Okay, so let me make 2 points here. One is that at if you look at the blue edge, the blue matching M2 W2, this happened because at some point in the algorithm W2 accepted M2's proposal. This is the only way that they could have gotten into an engagement, which is a prerequisite for them to get married at the very end. Okay, so at some point definitely W2 accepts M2's proposal. And on the other hand, it is also true that at some point M1 proposed to W1. Why is this? Because again, M1 is engaged to, M1 gets married to W1 at the end. And the only way this could have happened is if W1 accepted M1's proposal, which means that M1 did propose to W1. Okay, so we know that M2 proposed to W2 and M1 proposed to W1. But notice that M1 likes W2 better than W1, and recall that the proposals happened in order of preference, right? So the men are always going to be bold about their proposals. So they start with their most preferred person and then walk down the preference order. So what can you say at this point? If M1 proposed to W1, can we say that M1 must have also proposed to somebody? And what can we say about that somebody? And can you clinch the argument from here? It should be pretty transparent, but I'd just like to see somebody spell that out in the chat. Okay, I hope I haven't lost you guys completely here. I'm just going to wait for another minute or so just to see if somebody wants to formulate an argument here. Yeah, that's another way of putting it, that the M1 prefers W2 over W1 would not hold true if the proposal was made in order of preferences. One way of saying that is that given that M1 apparently likes W2 better than W1, before proposing to W1, M1 would have proposed to W2. Because we are going in order of preferences, right? So I'm just converting your contradiction argument to a more straightforward one, where we say that M1 must have proposed to W2 first. And what does W2 do? How does she react? Well, she likes M1 better than M2. At this point in the algorithm, maybe she has not gotten engaged to M2 yet. Maybe M2 has not proposed yet. We don't really know. But if you think about it, if M2 is W2's final partner, then all the proposals that W2 must have received throughout the algorithm must have been from men whom she likes less than M2, because if she received a proposal from somebody whom she likes better than M2, then either, so that proposal could have come after she received M2's proposal, in which case she would have broken off her engagement with M2, and gone with the better option, or it happens before she receives the proposal from M2, at which point she would have either accepted that offer or would have rejected it because she's already engaged to somebody even better. In any case, the point is that by the time M2 comes along with a proposal, W2 is already engaged to somebody better, and W2 would not have accepted M2's proposal. M2 may have proposed to W2, but it would not have been a proposal that would have gone through. That's the point, right? So it is simply not possible for W2 to have received a proposal from somebody, some man that she likes more than M2, because she's finally engaged to or she's finally married to M2. But on the other hand, we know for sure that M1 must have proposed to W2, because M1, before M1 reaches W1, he must have, because she's attacking the preference list in order of decreasing preference, he must have proposed to W2 before proposing to W1, and that is sort of that is sort of the contradiction. Okay. Yeah, Shreyasi is saying it is going as per one's gender preferences, so that their highest preference has to be unavailable. That is true. I mean, the only reason M1 had to go to W1 was because his higher preference W2 was unavailable, and W2 better be unavailable for a good reason, and the good reason should be that the person that she is currently engaged with is better than M1. So it cannot be the case that she actually likes M1 better than M2, right? So right. Okay. So, yeah. So, Dhaivat, I think we are on the same page with respect to the argument then. So, I think that sort of makes sense. So we have indeed shown that the resulting matching is stable. So let's just quickly run this on this one input example just to get a feel for what the algorithm is doing, and then we will finally get around to coding it. So again, correct me if I make any mistakes here, but let's just understand what happens, for example, in round one. So in round one, the men are going to propose. So one will propose to three. So three gets a proposal from one, and two will propose to two, and then three will propose to three. So three gets another proposal from three, and four will also propose to three. So right now, three is really spoiled for choice. And notice that 1 and 4 are simply missing from the top choices of the men. So 1 and 4 do not receive any proposals in the first round. So the current state of engagements is going to be that 2, of course, accepts the only proposal that she gets, because accepting a proposal is better than being single. Of course, coincidentally, she happens to have gotten a proposal from the best, from her top choice, which is great. But even if she had gotten a proposal from, say, 4, she would have still accepted it. As far as 3 is concerned, so I'm going to write this as woman on the left and men on the right, but hopefully that's clear. As far as 3 is concerned, she is spoiled for choice. She receives 3 proposals and she picks up the best one, which is 1. So at the end of the first round, the men who go back to being single are 3 and 4. Okay. So now let's understand what happens in round 2. So in round 2, 3 and 4 are going to propose to 1 and 2 respectively. So let's highlight those. So 3 proposes to 1, so 1 gets a proposal from 3, and 2 gets a proposal from 4. Of course, 2 is going to reject this proposal because 4 is her worst choice and she already is matched to her best choice. So it would be silly of her to even consider it. So 4 gets rejected. But 1 gets a proposal from 3, and one is not even engaged right now. 1 is single. So 1 is going to get engaged with 3. Okay. And now 4 proposes to 4 because that's going to be round 3. And this is the round where it's all going to end. Right now, notice that only 4 is single, and 4 is going to propose to 4 because 4 has been rejected by both 3 and 2. So 4 is going to propose to 4, and 4 for on the woman's side, this is actually a best possible match. So she's going to accept, even though it's the third. It's the third position on 4's list. Okay, so at this point 4 to 4 gets added to the stable matching. So So you can check that this is in fact stable, and let me also highlight only those that are matched, right? And now 4 is no longer single, so we are sort of done. So this is the final matching that you end up with. In this example, we did not really see a situation where a woman had to break off her current engagement to get to be with somebody, a fresh face that has just proposed that's better than her current partner. We did not see that phenomenon playing out, but you can imagine that could happen as well. So it could happen that for instance, 2 may have been engaged to 3 for some reason, and if then she gets a proposal from either 1 or 2, she'll break it off, and 3 will go back to being single, and then will have to continue making proposals. So from the men's point of view, being engaged once does not mean that you're engaged forever. You may have to go back to square one, back to being single. So men experience breakups in this algorithm, but the women don't. Notice that once a woman is single, once a woman is engaged, she stays engaged throughout the course of the algorithm. Of course, the partners may change, but it's never the case that she goes back to being single and then becomes engaged again. Okay, so was this example and the overall mechanics of the algorithm clear? Please give me a +1 if it is, and then we can move on to the implementation part. Rahul is saying 3 has to be matched with 3. Yeah, let's see. The thing is, 3 would love to be matched with 3. The man 3 would love to be matched with the woman 3. But as far as the woman 3 is concerned, she gets a proposal from 1 as well. Na? So she prefers 1. She likes 1 better than 3. So here the woman has the upper hand in terms of choosing the best proposal. That is why she gets matched to 1. And notice that there is no blocking pair here. So even though 3, so who is 3 currently matched to? 3 is currently matched to 1. So even though 3 likes 3 better, he is not going to be able to entice 3 into running away, because the woman 3 is going to say, oh look, but I have a better match, so why will I come with you? है ना? Okay, so yeah, Daiva, you have an excellent point. If the woman were to propose, maybe in this example it turns out to be the same. To be honest, I haven't worked it out, but that's a great point if it is. But it is indeed the case that these two matchings are typically not the same. And what is also interesting is that intuitively, although it seems like the women have the upper hand in this algorithm, in the sense that they are the one who are calling the shots and picking the best, and it seems like that, there is a formal sense in which the output of this algorithm is actually optimal for the men. So in some sense, among all possible stable matchings, if the men were to look at so there is no other stable matching where which is unilaterally better for the men, in the sense that there is no other stable matching where every man is as happy as they are in this one, and there's at least one man who is strictly happier. So that does not happen. So this is as good as it gets for the men, and there's a sense in which it can be really, really bad for the woman. And conversely, if the woman were to propose, then they would get the best possible matching from their perspective. And in some instances of this problem, these two matchings happen to be the same. In that case, that would be, in fact, the only stable matching in that problem. But otherwise, typically, you get a range of stable matchings. And in fact, there can be very many of them. And these two matchings that you get from this algorithm by either men proposing or women proposing are considered to be, in some sense, the two extreme matchings. And then there could be many other things in between. And this is like an entire field of research and algorithms. And people are even now trying to understand the space of stable matchings. It's a very intricate and a very interesting space combinatorially, and there's a lot going on there. So if anyone's interested, drop a line in the chat, and I will send you some links to or I'll add some links in the description where you can find out more about it. But if you want like a cute animated version of this algorithm itself, you can head over to Numberphile, where they actually discuss the algorithm and the proof of correctness, pretty much everything that we discussed up to this point, but of course with like nice brown paper and some cool animation, so you can check that out. And there are also a lot of stable matching simulators on the internet, so you can actually go and give your own instances and figure things out. As I said, this is a very, very fundamental problem. It comes up in anywhere you have to do an allocation, right? And you have preferences. This is something that just keeps coming up. So it's it's a particularly well-studied problem along with variations. And Rahul is saying this is partiality. That's correct. It does seem like this algorithm feels kind of asymmetric, right? But and indeed it is asymmetric. But to me personally, it's not asymmetric in the way that I would expect. Intuitively, I would have thought that the men proposing algorithm is good for the woman, but it turns out that it is not. What if two men and two women have the same ranking? So, well, I mean, I guess that's a possibility. Let's check it out. So they have the same ranking, meaning, so let me just try and understand. So, are there just two men and two women in the entire instance, and they all have the same ranking? I suppose. So, I mean, this could happen, in which case, so by the way, I don't know if this terminology is confusing. So let me see if it's better to use A and B for the woman and 1 and 2 for the men. So here are two men who have the same ranking, and here are two women who have the same ranking. So here essentially it is, I mean, so A and 1 are clearly like the more popular choices here, and the popular choices attract each other, right? So although both 1 and 2 want A, and if you want to make this a bit more explicit, you could even extend this. So let's say there is a very natural sort of ordering because of some popularity criteria. So I don't know if giving an example with IITs is too close for comfort, but you might imagine that most students will say, Bombay is our first preference, and then it's actually I don't even know enough to come up with a hypothetical example. But let's say if you go by JOSA closing ranks or something, most students would have that sort of a ranking. So this is a good example. I think it does come up in practice. And in fact, on the IIT side, everybody literally has the same ranking, which is the JEE ranking, right? So all of us are looking at the same ranking. So in this situation, what will happen is that the toppers will attract the toppers, right? So in fact, everybody will propose to A first, and A will get matched to 1 because she is going to pick her best preference. So that's what is going to happen. And then in the second round, 2 and 3 are both going to propose to B, and B is going to choose the next best option available. So 2 and B will get matched. 3 will propose to C, and C will get 3. So hopefully that makes sense. No? Right. So again, I think I'm going to sit through like this 10-second lag here, but let me know if this explanation with the 1, 2, 3 and ABC kind of made sense and if it clarified your question there. So there are a few examples which are really structured. I mean, one is that everybody has the same preference. The other would be when, as I said, the top is nicely distributed. So then you will, so let's say A had 1 as the top choice, B had 2 as the top choice, and 3 had C as the top choice. Then again, the ranking is very clear. A gets 1, B gets 2, C gets 3, and so on. And that's always going to be stable. Okay. All right. Cool. Okay. So, and as I said, I mean, these are some extreme examples. What is fascinating is that your rankings could be completely messed up and arbitrary looking and messy and all of that, but this algorithm still goes on to find a stable matching. I mean, it's a really, really elegant idea, and it's been around for a while, and I think it was one of the contributions that was a part of a Nobel Prize citation. So this is like, it's serious business here. But at the same time, as I said, it's something that's really ubiquitous by now. Okay, now I have a more practical question for you. I think it's been nearly an hour since the stream started. So are you up for coding this right now? I think my estimate is that it'll take another half an hour, but we could do it now, or we could break off and do a part 2. So For those of you who are tuned in, you guys are the victims. So let me know if you want to do it, if you have the appetite to do it right now, or do you want to break off and digest this a little bit and do it later. So just give me an hour later in the chat, and we will figure out accordingly. And one point is that you might want to think about these ideas and try to code it yourself, or you might want to be coding along like right now. So I'm good either way with whatever you suggest. Okay. Super. Those who wanted to say later are too late, I think. So I'm just going to I think few of you would like to check this out now, which is excellent. So let's go for it. Um, so okay, so let me get the notes out of the way because we are not going to be needing them. Um, okay, one thing that I think will be useful is to keep track of the problem. So in particular, okay, so I want to make sure that we can see the input and the output formats. Yeah, so one of these is exactly what we have already discussed as the running example, and then there's an additional example which is kind of lengthy. So I'm not going to discuss it explicitly, but I think the expected answer is essentially the output of the algorithm that we just discussed. So I'm going to leave it in here so that we can kind of validate our algorithm against theirs. Okay. Cool. So, as I said, feel free to spend this time coding along as well. I'm going to see if let's. Okay, so I'm going to be doing this from scratch. So I don't have any pre-written code. I mean, it's not the first time that I'm coding it up, but I'm going to do it from scratch along with all of you. So give me a +1 if you can see the screen and if the font size and everything is comfortable. I think for now we can ignore my terminal. So let me see if I can, yeah, get it to disappear. Okay. Okay, so at this point, I'm just trying to make sure that I collect the input. So notice that all of these are given to us as space separated lists of numbers. But there's this one slight annoyance, which is that I mean, it's not really an annoyance. I guess it's helpful. So notice that when n is 4, the sizes of the lists are 5. So the first number in the list is like the ID of the person whose preferences are being recorded, right? So we want to just keep that in mind. And there is a question of, I think in the beginning, you were suggesting how do we store these preferences? So it seems to make sense to store them as lists. But in some sense, I also want to get to the preferences of a particular man or woman easily. So I want to store those as dictionaries. Okay, so here's a dictionary each for men and women. And I would also like to store at any point the set of all single men, because we're going to say something like, while this list of single men is non-empty, we want to keep going. Okay. Um, yeah, so I think we may want to write down a separate function to solve this problem. So we may not need the single, thing here, but we'll see. So let's just collect um, this thing in a list. Again, this is just some Python junk for making sure that we get things nicely in a list of integers. I think for this problem, it doesn't particularly matter if we convert to integers or not, but I'm just doing it by force of habit. So what I want is in the dictionary for woman, the first thing is the key, and the rest of the list is the value. Okay. So let me just duplicate this and get this for the men as well. Actually, we could have just kept the same variable, but okay. Fine. Yeah, to begin with, let's also build up the list of single men. Now let's say we want to solve for n men. Actually, n can be derived, so let me not even bother with that. But let's pass the set of single men to this function. Okay, and let's just print this once to be sure that we have this okay. The only slight issue here is that, of course, I've not defined the solve function yet. And okay, so let me just define this anyway. Um, okay. Okay, so hopefully the terminal output is also visible to you, and you can sort of see that we do have these we do have these dictionaries, but one thing to be slightly careful about is that um, the we want the uh, top element of the list to reflect the top preference. So let me see what I mean by this. So suppose we have a list L, which is 1, 2, 3. So your top preference is 1, your second top preference is 2, and so on. If I do L dot pop, right? Um, what element do I get here and what element should I get here? So essentially for the men, what we will want to, what is going to be desirable is that we should be able to just pop from the list to recover the top preference. And basically we will work with that, right? So here, I mean, so here when we pop, we get in some sense the last element of the list as we see it here. So, to make sure that we are recovering the top preference, I'm going to reverse the list so that pop has the desired behavior. Okay, so here we're just going to, in anticipation of the use of pop in due course, I'm just going to reverse these lists so that in some sense when we keep popping from the list, we get the men and the women in the correct rank order. Okay, so far all we have done is we have collected the input and put it into dictionaries, and now we will actually implement the mechanics of the algorithm. But in terms of what we have done so far, just give me a quick +1 if things are clear, and let me know if there's something that, like if you need me to scroll up or down in the code, because from here I will just be focusing completely on implementing the solve function. So far all we have done is we have taken input, and that part should be clear. Yeah, it's actually I'm still getting used to what part should I focus and what shows on screen. So sorry about the erratic scrolling, but but hopefully this is clear. Okay. Okay, awesome. So I'm not dict of m dot pop of 0. Yeah, maybe we can pop elements at a particular index as well. That's a good point. Yeah, we could do that. Yes. Um, yeah, so maybe you can avoid the reversal by just using pop a little more carefully. But I'm just yeah, since I've done it already, I'm just going to stick to it. But okay. All right. So what do we need here? What we need is to maintain a list of, a list of current engagements and the set of single men. And also we need to know what is the current status of a woman, in the sense that when she receives a proposal from a man, we need to check if she's single or not. And based on that, we need to figure out if the proposal will be accepted or rejected. Okay. Okay, so let me just make sure that we have this. I'm going to maintain engagements as a dictionary. Again, we are going to say engagements of 2 is equal to 1 and things like that to signify that 2 comma 1 is now a pair. Okay. Let me also maintain a status thing. This is just to say that by default, all women are single, and if they get engaged, then we will just flip that to 1. Okay. All right. So the outer loop of the mechanism is just going to be that while the number of single men is greater than or equal to 1, or yeah, while there are still men who have not been engaged, we need to do this. And what do we need to do? So for each man in the set of single men, right, we will get this man to propose to his favorite woman in the current situation. So we're going to say top, that's the top choice. Let me even make it more explicit. Top choice is, so M of man denotes the preference order of the man under consideration, right? Remember, M is a dictionary which has whose keys are the men and whose values are the corresponding preference lists over the woman. So M of man will give us the preference list of the current man under consideration. And to get the top choice, we are going to just do a dot pop here. Okay. Now, what do we need to check? We need to check what happens when man proposes to top choice, right? So if So now again, we have to be a bit careful about the indexing business. So top choice is something between 1 and n. The status array has indices ranging from 0 to n minus 1. So if my top choice is woman 1, her status will be reflected in status of 0. So we are going to do status of top choice minus 1. Okay. So if this status is 0, which is to say the woman uh, that is man's top choice. Okay, sorry, I'm like confused between Python and C commenting. So, okay, so the woman that is the current man's top choice is currently single. Okay, that's what it means for the status to be 0. So in this case, what should I write? What should I do? In this case, the engagement goes through. So in terms of code, what are the things I need to worry about? I need to worry about the engagements dictionary, I need to worry about the single list, and I need to worry about the status list. Okay. And of course, there's also going to be an else. So here we need to check if this is playing out like a bad Bollywood film, but okay. So this is the else condition here. The else condition is that top choice is already engaged, and we need to know if the person who's proposing currently, if he makes for a better choice, right? Okay, so again, any suggestions in the chat are welcome. What is top choice minus 1? So this is the status array. The status array maintains, so let me just say this here. Status of I is equal to 0 if woman I plus 1 is single and is 1 otherwise, right? You can get away without maintaining an explicit status array by just looping through engagements to check if somebody is single or not. But I think it's simpler to just keep track of the status explicitly, because then it's quicker to check if somebody is single or not. Okay. All right. So top choice is, so let's say, for example, we are for man and single. So maybe it is the man is 3 and his top choice is 7. His current top choice is 7. Then we need to know, is woman number 7 currently single or not? And to do that, we would need to check the status array. But in the status array, we need to roll back the index by -1 so that we get the correct, we get the correct status, right? Uh, because otherwise, what are we looking at? Yeah, so again, as a simple example, if it's woman number one, the status array, status of 0 will tell you if woman number one is engaged or not. So that's why you need to do the -1. So hopefully that is clear, Meet. And as I said, if so again, any suggestions in the chat would be very welcome. But let me just, in the interest of time, go ahead and make the updates here. So if so this, as I said, here we are in the situation that the woman the woman is single, so this engagement should easily go through, right? So what do we do? Okay, thanks for the confirmation, Meet. So here what we are going to do is we make the engagement happen. So engagements of um, top choice. So we say that top choice is now engaged to man. Yeah, exactly what Dhaivat has said in the chat. We're going to make this engagement happen. And because this engagement has happened, both the man and the woman status need to be updated. So we're going to say single dot remove man and status of. So notice that now the status array will never go back to 0 for the woman. But for the man, we may have to put him back in the single array. We will see that that'll happen in the else part of things, right? So let me just free up a little bit of screen space here so that you can see more of the code. Okay, right. So what is going on? So this takes care of the if part. This was sort of the easy case. And in the else part, what do we need to do? In the else part, again, we cannot immediately make the engagement happen. We will need to check, we will need to check man versus top choice's current partner. So let's say current partner is, we get this from the dictionary. So engagements of top choice, right? And we need to somehow compare this current partner with man in W's preference list, right? So let me define prefs to be W of top choice. What is this? This is the preferences of the woman that man is proposing to, right? And now we need to check where does current partner appear in this preference list and where does woman appear in this preference list, right? So we want to say prefs of dot index of current partner versus prefs dot index of man. So let's just quickly recall how this works because I always get confused about such things. So I want to make sure that so remember that we reversed the list. We reversed all of these lists so that what is going on with the index. So let me just, maybe I said we won't need the notes, but because this is a key comparison that we are going to make, it's important to get it right. So let me just switch back here. So this list, let's say originally we took it as 2, 3, 1, 4, for instance. So let's say this is the woman's preferences, but in Python, this list is implemented as 4, 1, 3, 2. So let's say that this is the current partner, and let's say that this is the person who is proposing, right? So what is the index here? The index is 3, and here the index is 1. So if the index of the current partner is smaller, right, then the engagement will not go through, right? Okay, so yeah, so what we are saying is yeah, W of top choice dot index. So okay, engagements of top choice. Engagements of top choice is the current partner, indeed. So Dhaivat, you put everything together in one line. But the crucial thing that I want to double check is the direction of that inequality. So if this happens, if what you have written happens, should we go for the engagement? That's what you're saying. So the index of the person who is currently proposing. Okay, so no, I think this is why I said I want to be careful. So this is the original preferences, right? So this is the original preferences. And what I said is one is the, okay, sorry, I need to, I don't know how I jumped back so many pages, but okay. So in fact, one is the current partner and two is the person who's proposing. So in this case, the engagement should in fact go through. So if the index of the person who is proposing um, is larger, right? In that case, um, things should go through. Okay, in that case, the engagement should go through. So let me just encode that here. So if the index of the person who is proposing is larger, then that means that that person is closer to the top of the preference list than the person who is the current partner. Okay. So I just wanted to make sure that that part is okay. And is that what you have? Yeah, that's what you have as well. Great. So in this case, this goes through. I am not sure why I'm getting a warning here. So let me just write that out again. So if the current partner ka index is smaller and the person who's proposing their index is larger, here notice that we don't need to correct for like a +1 -1. It doesn't matter. It's just the relative order that matters. So in this case, the engagement should go through. So again, engagements of top choice equals man, single dot remove man. So man is no longer single. But notice that we don't need to do anything for status of top choice because she was already engaged before. She remains engaged now. But there's something else that we need to do. And that is crucial because an engagement was broken here. So what do we need to do? Okay. Also, I'm going to do a little bit of bookkeeping while you guys tell me in the chat what else I should add there. I'm going to create a marriages dictionary because right now the engagements dictionary map the woman to the man. But if you go back and look at the problem statement, you will see that what we require to output is the matchings from men to women. So the format of the output is that you list all the men from 1 to n, and for each man you list the partner woman. Okay, so let's reverse this dictionary, which is to say that reverse it, invert it, whatever you want to call it. So if you look at engagements dot items, these are woman man pairs. What I want to do is I want to turn it into man woman pair. So marriage is on M equals W, and this is what we want to print. So notice that the IDs of the men range from 1 to n. So we need a range going from 1 to n plus 1 in Python. And what do we want to print? We want to print man and marriages. Who did man finally get married to? Um, And yeah, great point. We need to, so the person, so current partner here has a raw deal, was thrown out of an engagement. So that person is now single again. So we removed man from the single array, but we need to append current partner to the single array as well. Okay, so we do need to do this. And I think that's all that we need to do. As I said, the status, the status of the woman who is top choice is not affected because she was engaged before, she remains engaged now. And let me scroll down a bit so that you can see the final output. So as I said, we are inverting this dictionary so that we can get, so the dictionary tells us for every woman who is the man that she is partnered to, but what we need to print, a little annoyingly, is for every man we need to print the woman that he is partnered to, so, or he's partnered with. So I think we did a fair amount of like writing things. Let's do a quick test. I did say that this will take about half an hour. We are around that point here. Um, so let me. Okay. So in particular, let me run this on the two examples that we have. Okay. Let me- So I am not okay. Let me just quickly double check the code here for. Okay, I did not quite test what I was doing after reversing the dictionary. I mean, after reversing the list. Hopefully, there isn't a problem there. Is anybody coding along that's suffering as well? Okay, sorry. The print code is out of view. One second. Oh, you probably cannot also see the output. Let me try and fix that. No, so we have called the function, but it is true that this stuff does not need to be inside the while loop. I think once the while loop is done, we come out of it. Okay, no, I think this is fine, except that I forgot to make sure that you can see the output. So let me just enable this. Okay. So let's just tally this quickly with the expected outputs. So we have the last 7 lines. So 1 to 4, 2 to 5, 3 to 1, 4 to 3, 5 to 7, 6 to 6, and 7 to 2. So this is as you would expect. And for the first input, I think the printing is a bit messed up because of the way I pasted the code. But this is I think this is the marriage that we are looking at. 1 3 2 2 3 1 and 4 4. Yeah. Okay. So this seems reasonable, and I think this, what I've written here, is very close to something that I had tried submitting on Codechef recently. So if you, again, as I said, if you've been coding along, you could, you could try submitting your version and checking if it works. I think it does get this code, as far as I know, does get accepted by the judge. The only question is, do you want some live evidence? So I think, um, oops. Okay, let me first submit and then I'll fix what's happening on the stream. Um, okay, I think the reason I'm getting a runtime error is because I checked custom input, but I didn't actually give any input. I'm just going to be brave and I'll just submit it and see what happens. Okay. So I guess, as you can see here, this seems to check out. And it's not surprising. I think we have, I mean, barring, of course, like coding quirks, we have implemented exactly the mechanism that we discussed and that we proved was correct. So, and as I said, give me a +1 if all of this makes sense to you. And yeah, and Meet, special thanks for pointing out that the for loop was indented way too much. And Dhaivat, thanks for predicting the codes as we went along. That was very helpful. And as I said, you can try this out and maybe uh, try coding it yourself, because this is very much doable once you have the mechanism. I think coming up with the mechanism is it's not obvious, but once you know what it is, I think it's fairly clear how you can go how you can go ahead and code it. Okay, I think the stream ended up being longer than I had originally planned. So really appreciate all of you staying back all the way. And thanks so much. Hopefully this is a bit of a bit of a trailer for what's coming up, the format of DSA2. And I think I'll any suggestions or any thoughts that you have about what you would like to see would be very welcome. You can send me a message. Most of you who are here kind of know how to reach me, or feel free to drop in a comment on this video. I'll be happy to take a look. It could even be stuff like, can we add some background music or whatever? So, and any suggestions, wide ranging, are welcome. But this was great fun, and maybe we'll do a couple of more sort of warm-up streams before we actually formally start with classes. I don't know if so in DSA2, I think it would be useful, and for competitive programming in general, I think it would be useful to have some comfort with C++. I think I kind of clubbed this stream to also be a bit of a farewell stream for the class that just finished computing. I don't know how many of you are here from ES102. Give me a shout if you are. And so I kind of decided to stick to doing this in Python. But I think in general, we might be gravitating towards C++ a lot more. So maybe there'll be a couple of streams where we just get comfortable with the mechanics and the common libraries of C++. That's something I'm tentatively planning. But any other thoughts that you have would be welcome. But for now, let me wrap up the stream here so that you guys can, get to lunch or whatever other plans you have. Once again, this was fun. Thanks for sticking around, and bye for now. Yeah.